Hello and welcome to the Unit 1 podcast. We're continuing section 5.1. It was so big we decided to break it up into two.
So here we are again. I am Mr. Lin.
I'm Mr. Sakaguchi, and now we're going to talk more about light and how it relates to electrons. So last podcast we talked about the wave nature of light. Back in earlier days, in the early 20th century, there were two camps. Some believe, light is a wave, and some people thought light was a particle. And light has properties that you could argue either side. And this is very controversial during this time. Heated objects, when you heat them up, only emit certain frequencies of light. So for instance, like if you've ever seen movies where there's a blacksmith pounding on metal for horseshoes or for swords or whatever, you'll always notice that there's yellow, reddish, or sometimes white or bluish light, but you never see any other different kinds of colors.
A great place to see examples of different colors of heated light would be fireworks on the 4th of July. All those different colors are from different elements being lit up.
So part of science is basically taking things you observe and trying to quantify them. So, Planck and Einstein were trying to figure this stuff out. So everyone knows Einstein's equation, E equals mc squared, but Planck's equation was just as important. And what they found is that Planck's equation, E equals hv, finds that the energy has certain frequencies. E is the energy of the light, h is a constant, and v, as we know, is frequency.
And so different amounts of energy resulted in different colors of light or frequencies of the EM spectrum.
So if you combine Einstein's and Planck's equation, you can actually see that light can have particle-like properties, because if we substitute mc squared for E in Planck's equation, we can actually solve for mass. So there is the conundrum right there.
So first up, you'll notice that I discussed earlier with the fireworks that metals give off different colors when heated. All right. Now the reason for this is something called the quantum, and that results from the amount of energy that can be gained or absorbed by an atom and then later on lost. When the atom loses that extra energy, it releases that quantum into something called a photon, which we'll discuss later.
Now, the reason why the quantum is such a revolutionary idea is because people are basically, just like how people in physics felt either light was a particle or a wave, a lot of people are in two different camps in terms of the way they looked at energy. If you were more of a Newtonian person, the idea that energy is indivisible forever. In other words, according to Newton, you should be able to take energy and cut it in half forever. Whereas the concept behind quantum is that you get to a point where you cannot cut the energy in half anymore. That's what the quantum represents. It's like the atom for energy. It's the smallest unit for energy.
And because if they're in these discrete packages, it becomes easier to count them, to measure them. So that's why the quantum concept was so important. Because now that it's measurable, you can start exploring it into more detail.
So basically, this kind of was shown by Planck with his equation. He was able to show that if this quantum concept is in fact true, his equation should work, and that's why certain metals only gave off certain kinds of waves, because of the way the energy is packaged, so to speak.
Right. So here we come to something called the photoelectric effect. Okay, so what happens here is when a metal is absorbing energy or gets hit with energy in the form of light, it will absorb that energy and then re-release some of the energy as light again, but it will be changed. You'll see in the diagram here, this is just a representation of just a full spectrum of energy or light, but then what comes off are very, very specific packages.
For electrons.
Yeah, electrons.
Well, they're called photoelectrons, right?
Right.
So the idea here is that certain metals, basically, if you shine a certain kind of energy with a minimum frequency, that these metals will eject electrons from the metal. So this is kind of like some of the background that led to solar energy. Okay, basically it's an application of Planck's theory, and this is actually what Einstein won the Nobel Prize for. He was able to show that this energy could actually from waves could actually cause matter to move. So if you think about it, moving electrons are essentially what electricity is. And so what they found is that if I shine more light on this metal, you'll get more electrons, but the energy that they carry doesn't change. Whereas if I have a higher frequency light, a more intense light, the electrons come off, but they'll have a greater energy.
And the difference between how much electrons get ejected is not so much on the amount of light, but actually the frequency and its inherent energy.
So this was the experiment that kind of showed that light and a lot of other particles have both wave-like and particle-like properties. And so it ushered in a whole new era of physics known as quantum physics.
Now, the applications of the photoelectric effect are actually all over the place. The LCD screen that you're watching this PowerPoint with is actually an extension of the photoelectric effect. Electrical currents run through the material and out comes light. It's the reverse of what the equation is doing. So because of this, we get things like our cell phones, LCD screens, calculators, etc.
All this kind of relates back to the atom through something known as the atomic emission spectrum. And this is basically a set of frequencies of EM waves that atoms give off when they're heated.
One thing to keep note of is that each different element, when it is energized, is going to give off a unique spectrum of light. So certain elements will light up one color and certain other elements will light up another. And this is because of the elements' electron configuration, how the electrons are set up, how they absorb light, and as a result, how they release light will give off a different energy amount, a different frequency. And that frequency, if you remember the EM spectrum chart from the previous PowerPoint, will associate with a different color of light.
Yeah, so the idea here is that if only certain kinds of frequencies of light are given off, that means there has to be some level of organization to the electrons within an atom. And this is why only certain frequencies are seen. It also kind of gives credence to the quantum theory in the sense that only certain packets of energy, of EM energy, are actually observed. Again, kind of adding to the whole idea of quantum. What this figure is
Illustrating.
It's showing the emission spectrum for hydrogen. Now, there are different series here. So there's a Lyman series, a Paschen series. These are emissions that are not seen by the visible eye. The ones we're going to focus on are the Balmer series, the colors you see. Basically, what we see is as you heat up an element, it's absorbing energy. And electrons are absorbing energy, and that causes electrons to move from what we call their ground state to higher energy levels. But they don't stay there forever.
What goes up must come down.
So as they fall back down, they release the energy they absorb to get to that higher level. And that energy release we see in the form of visible color, or what we call photons. And so as they fall, they give rise to particular frequencies and wavelengths.
Because they fall different distances, quote unquote, they each have different energies, so different frequencies.
But what's important to note here is that no matter where the element comes from, as long as every hydrogen atom will basically behave in this exact same fashion. And if we went on and examined other elements, we would find that they would have other characteristic spectrums
but each unique for each element, and that's how you can identify different elements.
And we will be doing that as a lab soon. And until next time.
I left out the vomiting part. It just didn't flow.